In Inner Mongolia and northeast China lies a vast sandy region known as the Hawkin Sandyland, covering an area of roughly 50,000 to 60,000 square kilometers, about 9 times the size of Shanghai. Over hundreds of millions of years, granite formations have weathered and broken down. The resulting particles were transported by rivers, then further sorted and redistributed by wind, eventually forming the largest silica sand deposit in China, the Hawkin Left-Wing Banner Silica Sand Mine. The glass-grade quartz sand produced here contains up to 96% silicon dioxide and extremely low levels of iron oxide, making it especially well suited for manufacturing the focus of this episode, automotive glass. With the rapid rise of new energy vehicles, the glass above our heads is getting larger and larger. Letting in more light has become a defining trend in modern automotive design, but brightness comes at a cost. This is the Sun, the closest star to us, located about 150 million kilometers away. Its photosphere, only about 500 kilometers thick, has a temperature of roughly 5,800 Kelvin. The solar spectrum we receive can be approximated as blackbody radiation at 5,778 Kelvin. After absorption and scattering by the atmosphere, the solar irradiance at the Earth's surface reaches about 1,000 watts per square meter at noon. Take the Model 3 as an example. Its panoramic roof alone covers nearly 2.2 square meters. Including the projected area from above, along with the windshield and rear glass, the total comes to about 4.5 square meters. At noon, if all that glass were to absorb the sun's energy, it would amount to roughly 4,500 watts of heat, equivalent to running 5 space heaters inside the car. That's a lot of heat. To keep this heat outside the vehicle, we turn back to the solar radiation spectrum. Using the limits of human vision, approximately 380 nanometers at the lower end and 780 nanometers at the upper end, sunlight near the Earth's surface can be divided into 3 regions: ultraviolet, visible, and infrared. Ultraviolet accounts for the smallest portion of solar radiation, contributing only about 5% of the total energy. Ozone, which we're all familiar with, strongly absorbs ultraviolet radiation below 280 nanometers, but absorbs very little beyond 315 nanometers. Based on this, the ultraviolet spectrum is typically divided into 3 bands: UVC, UVB, and UVA. UVC can directly damage biological DNA and has powerful sterilizing effects. Fortunately, it is almost entirely absorbed by atmospheric oxygen, so its impact at the Earth's surface is negligible. UVB is responsible for sunburn and increases the risk of skin cancer. However, most of it is absorbed by the ozone layer. The small fraction that reaches the ground accounts for only about 5% of total ultraviolet radiation, and it cannot penetrate glass. In contrast, UVA, with wavelengths between 315 and 400 nanometers, makes up the majority of ultraviolet energy. A well-known case published in the New England Journal of Medicine in 2012 documented a truck driver with 28 years of driving experience, showing pronounced unilateral photoaging caused by chronic sun exposure. So, if glass cannot effectively block UVA, what can? To answer this question, we need to draw on some concepts from solid-state physics. From high school physics, we know that electrons in atoms occupy discrete energy levels. When the energy of an incoming photon matches the energy difference between these levels, the photon can be absorbed, allowing the electron to transition to a higher energy state. When vast numbers of atoms come together to form a crystal, the originally discrete atomic energy levels broaden into continuous regions known as energy bands. The lower band is called the valence band, while the higher, unoccupied states form the conduction band. The energy difference between these 2 bands is known as the band gap. From this diagram, we can see the energy associated with an individual photon. The float glass used in automotive applications is a type of soda-lime silica glass. Due to the presence of numerous impurities and structural defects, its band gap typically falls in the range of about 3.5 to 4.5 electron volts. This range already covers nearly the entire UVB spectrum and even extends into part of the UVA region. So how do we block the remaining UVA? Organic materials provide an effective solution. With abundant CO bonds, CC bonds, and hydroxyl groups, their band gaps align well with the energy range of UVA absorption. In engineering practice, polyvinyl butyrol is commonly used as the interlayer in laminated automotive glass for UV protection. Its electronic transition energies fall roughly in the range of 3 to 6 electron volts, while still maintaining high visible light transmittance and long-term durability. So in the end, UVA is handled by organic materials, UVB by the glass itself, and UVC by the atmosphere. Ultraviolet radiation, problem solved in no time. Now let's move on to the second component, visible light. It accounts for about 49% of solar radiation, making up the largest share of the sun's energy that reaches us. Even if you had some kind of magical glass that could perfectly block all ultraviolet and infrared radiation, you would still be dealing with the heat equivalent of 2.5 radiant heaters. Where there is light, there is heat, and where there is heat, there is light, right? As early as the 19th century, it was recognized that the human eye does not perceive all wavelengths of light equally. Perceived brightness is not the same as radiant intensity. So how do we quantify visual brightness? Consider a reference light source with a wavelength λ1 and a test source with a wavelength λ2. When the two alternate slowly, you perceive a flicker between red and green. But as the flicker frequency increases to around 15 to 20 Hz, the color alternation becomes indistinguishable. What you see instead is a single blended color with only a variation in brightness. Once the visual brightness of the two sources is closely matched, the flicker disappears entirely to the human eye. At that point, if the measured radiant intensity of the test source is 10 times that of the reference source, it means that the visual efficiency of wavelength λ2 is 1/10 that of the reference wavelength. In 1923, Gibson and Tyndall used this very method, known as flicker photometry, to derive the average luminous efficiency curve of human vision. It shows that the human eye is most sensitive to green light at 555 nanometers. Even when red light at 650 nanometers has a radiant intensity comparable to that of 555 nanometer green light, it is perceived as only about 1/10 as bright. This makes the problem a bit more manageable. By slightly reducing the perceived brightness inside the cabin, we can significantly cut down the energy carried by visible light. For wavelengths near the ultraviolet, adjusting the composition of organic materials can reduce the band gap, allowing them to absorb longer wavelengths. But when it comes to the infrared, the challenge is much greater. Can we find a material that remains transparent to visible light, where photons carry higher energy, while effectively absorbing lower energy infrared radiation? This remains a key challenge for automotive engineers. Silver, a common highly conductive metal, when we zoom into its structure, we find a lattice of positively charged metal ions arranged in a fixed periodic pattern, surrounded by electrons that can move freely. This is the foundation of the free electron gas model in solid-state physics. When an electromagnetic wave reaches the surface of silver, the electric field of the incident light drives the electron gas to oscillate back and forth against the background of the ionic lattice. This oscillation generates an opposing electromagnetic field, which, at the macroscopic level, appears as reflection. If the frequency of the incoming wave is too high, the electrons cannot respond quickly enough to follow the oscillation. Conversely, at lower frequencies, corresponding to longer wavelengths, the electrons can respond more effectively. In principle, this means that reflectivity in the infrared can be stronger than in the visible range. And this is indeed the case. In 1972, Johnson and Christie measured the refractive index N and extinction coefficient K of silver using ellipsometry, as reported in their classic paper, Optical Constants of the Noble Metals. From the Fresnel boundary conditions, the reflectivity of metallic silver can be derived accordingly. A smooth silver surface reflects about 97% of visible light, while in the near-infrared, around 1,500 nanometers, its reflectivity approaches 99%. The remaining few percent of the energy is absorbed within the metal. At first glance, silver seems like an almost perfect reflector. More importantly, it reflects infrared light even more strongly than visible light. However, a reflectivity of 97% is practically opaque. So, is there a way to make silver transmit visible light? There is. Make the silver layer thin enough. Electromagnetic waves do not vanish instantly inside a metal. They decay exponentially. The depth at which the amplitude drops to 1/e, about 37% of its original value, is known as the skin depth. Using the extinction coefficient K, measured by Johnson and Christie, we can calculate the skin depth of silver at different wavelengths. In the visible and near-infrared ranges, where most of the solar energy lies, the skin depth is typically around 11 to 15 nanometers. This means that if we compress silver into a film about 10 nanometers thick, it can transmit a significant portion of visible light, effectively making the metal appear transparent. At roughly 10 nanometers, we are already approaching the lower limit of current fabrication techniques for forming a continuous silver film, equivalent to stacking only about 35 layers of silver atoms. In a vacuum environment, inert argon ions are accelerated to bombard a silver target. The ejected silver atoms then deposit onto the glass, gradually forming a nanoscale silver film. This process is known as magnetron sputtering, a technique widely used in industry. In practical manufacturing, the thickness of the silver layer can be controlled with an accuracy on the order of 0.5 nanometers. In a report published in 2021, researchers measured the optical properties of a 10 nanometer silver film. Across the visible spectrum, its reflectivity remains generally below 30%. Around 555 nanometers, the wavelength to which the human eye is most sensitive, its transmittance exceeds 50%. In the near-infrared, however, reflectivity rises above 50%, while transmittance drops to around 10%. It lets nearly half the visible light in, while stopping most of the near-infrared. That ultra-thin 10 nanometer silver layer is the real hero here, keeping a tiny 3 square meter cabin both bright and comfortable. Can we go even further? Add another layer. With a double silver coating, infrared reflection becomes even more effective. Meanwhile, by carefully tuning the thickness of dielectric layers, multiple Fabry-Perot cavities can be formed. Through interference effects, transmittance in the visible range can be enhanced. As a result, visible transmittance increases from about 50% for a single silver layer to around 60%, while near-infrared reflectivity reaches roughly 90%. Add yet another layer. With a triple silver structure, visible transmittance can be further improved to around 70%, while near-infrared reflectivity climbs to about 95%. At this point, you've finally engineered a sophisticated composite transparent material, one that absorbs ultraviolet, transmits visible light, and blocks infrared radiation. Thanks for watching our first episode. Don't forget to subscribe and let us know what we should cover next. Here's a question for you. Considering the skin depth of centimeter wave and millimeter wave signals used in mobile communications, do you think silver-coated glass would interfere with your phone signal?